Okay, so here we are. This is the third attempt actually at this particular example. Not because I got it wrong, but because I failed with the technology. So here we go, let's try again. And hopefully this time it will work. So this is the equation of trajectory that we're really looking at here. Yeah, it's a very good example of an exam style question where they ask you to show a particular result, and then the second part of the question is to use the result to answer the question. So here we go. A particle is projected from a point with speed u. So projected, speed u, angle of elevation alpha, so that's the angle above the horizontal, and moves freely under gravity. So we see that freely under gravity phase, and we know that we're going to be in a SUVAT or constant acceleration kind of context. When the particle moves a horizontal distance x, the height above the fluid projection is y. So we can illustrate that on a diagram. We've got an initial speed u at an angle alpha to the horizontal, and it's going to follow a projectile motion path, and we're really talking about particular points x, y, where our x-axis is the distance across and our y-axis is the vertical displacement. So we can come down here then and start to use our standard approaches. Constant acceleration, because we were told that it's moving freely under gravity. So there's a key phrase, and it doesn't matter which we choose to look at first, horizontal or vertical. So if we take the vertical motion, because we're trying to find the y equals something. So let's see what we get. U, vertical. Well, we need to break our speed down into our initial velocity down into two components. We have a vertical component, which is u sine alpha, and we have a horizontal component, which is u cos alpha, because it's next to the angle. So uy is u sine alpha. We've got an acceleration, which is negative g, because it's acting downwards. Don't forget that. We want its vertical displacement, s, which we're calling y. And we don't know t, and we don't know v. But if we want a statement to do with s, its position, it's probably best to use something to do with u, a, s and t. Come on, David, I'm sure you know that by now. I hope you've remembered it. S is equal to ut plus a half at squared. Once we've stated, you know what happens next, we substitute in. So we get y is equal to u sine alpha t plus a half negative g t squared. Tidy that up, so y equals u sine alpha t minus g over 2 t squared. Now, if we look at this equation, there's not much that we're happy about, but there are a few bits. So we can see what we've got the g over 2. We can see that we've got the y, but not much else. Also, if we look at the equation here, we can see it's got no t in it. Yeah? There's no t. Therefore, need to eliminate t from our first equation, from 1. So this is our equation 1 here. So how can we get rid of the t? Well, we're going to need another equation. We can then consider constant acceleration horizontally. And we're going to get ux, which is u cos alpha. A is equal to 0. S is equal to x. And t is the same time as we used before. U, A, S and T, well, we've already got the equation for that, so we can substitute straight in. X equals U cos alpha T minus or plus 0 for the half AT squared bit, because there's no acceleration. Now, we've already identified that we need to eliminate this variable T from the equation. Yeah, we want to eliminate this T using our horizontal motion equation for the horizontal motion. Yeah, so it's this T that we're going to make the subject. So we get T equals x over u cos alpha, and then we just substitute into 1 in the usual way. So we get sub in 1 as we planned, and we're going to get y is equal to u sine alpha, and then t, but instead of t we've got x over u cos alpha minus g over 2 and x over u cos alpha squared now. So let's tidy that up. The u's here will cancel, and we've got sine alpha over cos alpha, which we can write as tan alpha, so we get x tan alpha minus g over 2 times x squared over u squared cos squared alpha. Now, in the pure maths, which is to come, 1 over cos squared equals sec squared, and this is something we're going to have to learn if we don't already know it. So 1 over cos alpha equals sec squared alpha. Learn. Therefore, 1 over cos squared alpha is sec squared alpha. I've got a mistake written now. I've written the squared in up there, but we need to get rid of that. So 1 over cos alpha equals sec alpha, and 1 over cos squared alpha equals sec squared alpha. So we've now got y is equal to x tan alpha minus gx squared over 2u squared sec squared alpha. Okay, so that's come from here, substituting in there. So we've now got to get rid of, if we look back at our original target, we've got everything that we need now. X tan alpha, which is what we want, minus gx squared over 2u squared. But instead of sec squared, we would need 1 plus tan squared alpha. So that comes from another equation, which you are familiar with, I hope. Sine squared theta plus cos squared theta is identical to 1, true for all values of theta. Divide through by cos squared theta, and we get tan squared theta plus 1 equals sec squared theta. So now we can substitute using this bit in for sec squared. And we're going to get now y equals x tan alpha minus gx squared over 2u squared 1 plus tan squared alpha as required. And although that seems very complex, the work we've done there is very, very similar to lots of the more standard questions we've already done before in terms of its approach. So, part B. Now B is almost certainly going to be using that equation because we've shown that, so we're likely to need it. Let's see what we've got here then. So, we have a particle projected from a point O on a horizontal plane with speed 28 at an angle alpha, which passes through a point B which is at a horizontal distance 32,8. So 32 along from O and 8 above the plane. Find the two possible values giving you answers to the nearest degree. Okay, so part B. We have got a speed of 28, still at an unknown angle, alpha, and we want to know when it passes through the point 28, 8. What am I mixing up? That's 32 there, isn't it? So it's going through the point 32, 8. Make sure I've got that right. Yes. Okay, so it's doing this. And we're looking at the values of alpha which will enable that to happen. Because it could be on its way up, or it could be on its way down as I've drawn it out, or it could be on its way up. So there are two positions, two ways that could, it could occur so it goes through it on its way up, or it could happen so it goes on the way down. So that height is 8, that height is 8. I'm not sure that's the best drawing. Let's just rub that out and try it again. Yeah, so I'm going to get rid of that drawing, sorry, and let's just think about that a little bit more carefully. So just learning to use the software again, cut. Okay, so back again, let's try again. So we could either have something which goes up and down through the point, or we can have something that does that kind of thing through the point. So there are two angles here, alpha, which it could be thrown at to go through that one point, which would be 8, trying to remember what the numbers were. I think it was 32 and 8. Either way, the speed initially is 28. Our equation of trajectory, which we've just worked out, was y equals x tan alpha minus x tan alpha minus gx squared over 2u squared times 1 plus tan alpha. So what we know is our point xy, because that's going to come from here, and we know our value u, so that only leaves one unknown in the equation, so we can substitute in. So we get 8 equals 32 tan alpha minus g over 2 x squared, which is the 32 squared, over u squared, which is 28 squared times 1 plus tan alpha. 1 plus tan squared alpha, wasn't it? 1 plus tan squared alpha, I've misremembered that. Okay, that's correct now. So, we can now form a quadratic from that in the usual way. We want it to be a positive quadratic and equal to 0. Yeah? How do we know it was a quadratic equation? Yeah? Well, we've got a squared there and a linear term there. And alpha is our only variable in the question. So we've got a quadratic in tan alpha. So let's just tidy up the numbers a bit. 8 equals 32 tan alpha minus g over 2. Well, 32 over 28 is the same as 8 over 7 squared times 1 plus tan squared alpha. We could keep working on that. 8 squared is 64, so that's equals 32 tan alpha minus 64 over 2 is 32g over 49 times 1 plus tan squared alpha. And then we could multiply through by 49. So we get 8 times 49 equals 49 times 32 tan alpha minus 32g minus 32 tan squared alpha. So we've got it all on one line. Usual approach, then make it positive and equal to 0. So it's a quadratic, positive equal to 0 is what we want. So we're going to get 32 tan squared alpha minus 49 times 32 tan alpha plus 8 lots of 49 plus 32g equals 0. Now you'd have a calculator at this point, tap it in and you'll get two solutions. Yeah, so tan alpha is equal to a half or 9 over 2. So you'll get that from the calculator. So alpha equals arc tan of a half, or alpha equals arc tan of 9 over 2. And those come out to be approximately 30. If you tap it in, I think you'll get it more accurately than that, 27-ish. And alpha is equal to 77 degrees. Right, and if we look back at the diagram we drew, so this one here is equating with the 77 degrees, so it's going higher and then coming down to the point B, and this one here is equating to the 27 degrees, so the green is the 27 degrees and the blue is the 77 degrees, both of which lead to the particle going through the points 32, 8. I hope that's helped. And then we need to set some work attached to that. So the work that I'd like you to do based from that exercise is exercise 6D, questions 5 through to 5, 6, 7 and 8. Okay. Any problems, let me know and I'll see what else I can do to help. Okay.